Hello, so today we are going to do this problem, which is part of Leetcode daily challenge. Find the minimum and maximum number of nodes between critical points. So basically a critical point in a linked list is defined here as either a local maxima or a local minima. And what they mean by local maxima is if the node that is local maxima, the previous node needs to be smaller than it, and the next node needs to be smaller than it. So basically, it needs that this node needs to be the greater than the previous one and the next one. So an example can be if the current node is 5, the previous one is 2, and maybe the next one is 3, then this one is a local maxima because it's bigger than the previous one and bigger than the next one. Okay. Local minima is the same thing except instead of greater, it needs to be smaller. So it needs to be, let's take an example. 1, for example. Let's say the previous one is 2, the next one is 3, then this one is smaller than the next one and smaller than the previous one. So it's a local minima. So already you can see that for the element to be a local minima or local maxima, it needs to be either it can't be the first node and it can't be the last node, because the last node doesn't have a next node and the first node doesn't have a previous node. Okay. And once we determine we go through the linked list and find all the local maxima and the local minima, each of these, both are considered a critical point. So we need to know the position of these critical points and then calculate the minimum distance between any two of these critical points and the maximum distance between any two of these critical points. Okay, so obviously for the maximum distance, it's going to be between the first critical point and the last critical point, because that would be the max. If you take anything else, it would be closer and it won't be the max. For the minimum distance, that depends. We need to look at every two adjacent critical points and take the minimum distance between all of them, right? So let's take a look at this example because it's a little bit longer, so it would be more useful. So for this one, we can just go through the linked list element by element, right? Except since we know the local minima and any critical point candidate can be the first and last, we can just start from here. But we need to keep track of the previous node and we need to keep track of the next node. Okay, and so we'll look at 3. Is 3 a local minima, which means it's smaller than both the previous and next. It's smaller than the previous, but it's not smaller than the next. So it's not a local minima. Now, is it a local maxima? No, because it's not bigger than the previous. And so it's neither, so it's not a critical point. So this one is not a critical point. So we move here, which means this one becomes previous, and this one becomes next. And so we compare, is one a local minima? Yes, it's smaller than the previous, which is 3, smaller than the next one, which is 2. So it is a local minima. So now our critical points need to have the position. Remember, we are interested in the distance between the critical points, so we only need to keep track of the positions. And so here we can keep track of the positions. And the position here would be 0, 1, 2. Okay. And now we look at we move again. Now, if we find that it's a local minima or local maxima, we just need to check for one of them. We don't need to check for the other because it can be both at the same time, right? Okay, so now we move here. We move to this one. Okay, so now we look at the next one. So this becomes the previous one, and this becomes the next one. Now, is 2 a local minima? No, because it's not smaller than 1. Is 2 a local maxima? No, because it's not bigger than the next one, which is 5. So we move on. We go here. Now our previous becomes this one. Now notice here, every time we move current to the next one, so current is now equal to current.next, and we move pref to the position current was in, and we move next to the next position. So while traversing, we need to do all of these 3 operations to move all the 3 pointers that we need. And so here our previous is now at 2, our next is now at 1, and we compare. Is 5 a local minima? No. But is it a local maxima? Yes, it's bigger than 2, bigger than 1. And so we add it to our critical point. Now what's the position? 0, 1, 2, 3, 4. So position 4. Now we look at the next one, which is 1, and this becomes our previous. Is 1 a local minima? Yes, it's smaller than both. Is it a local maxima? Of course not, but it is a local minima, so it is critical point, so we add its position, which is position 5. And now we can just take a look at, to get the maximum distance, it's just the first minus the distance of the last minus the first, so it's 3 for the maximum distance. Now, what about the minimum distance? Well, with minimum distance, we just need to compare the adjacent numbers, right? We don't need to compare 2 against 5 because we know the one in between would be a smaller distance, obviously, right? So we just need to compare 2. This one, the distance is 2. This one, between the 2, the distance is 1. Between 4 and 5, so it's 1. And so we return this. Okay, so that's pretty much it. Very straightforward one pass traversal, but you need to keep track of the pointers and add to a list the critical points. Okay, so now let's just code this up and make sure it passes. So first, what we need to do here is we need a couple of pointers. We know we need the previous, the current, and the next one. So the previous can be the first node. The current is the next one. That's the only potential candidates for a critical point. And then the next is the next of all of them. Now, one thing in the constraint here is that the number of nodes is at least 2. So we know that this will pass. This maybe is nil. So we may get next is nil, but we can check for that in our while loop. But we also need to keep track of the position, the candidate position, because this is what we'll keep track of in the critical positions, right? So critical points, let's call them. We will keep track of the positions. Let's call them critical positions. Okay. Now why is position 1? Because remember, the candidates can be only current. So this is the position pointing to the current node. So points, let's call it current position. So that it's clear that it's the current node's position. And so we do while, basically current and next. Because we know if next is nil, that means current is at the last position, which means it can't be a critical point. And actually, we can just do while next. So first we check if it's a local minima, and then we can check if it's a local maxima. So we check for a local minima, and then after that we can check for a local maxima. Okay. And now what we need to do is just do the same checks we did. So first we check if it's a local minima. Now, what is a local minima? It means the current node needs to be smaller, the value needs to be smaller than the previous value and smaller than the next value. That's the definition. Okay. Now, if this is the case, it's a local minima. Similarly, for a local maxima, it needs to be bigger than both. So greater than previous and greater than next. Now, if it is, then we want to add it to this one so that we can later get the mean distance. So we can just add the position, which is current position. Same thing here. Now, the other thing we need to do is advance all of our pointers. So first, we know the position needs to advance by 1. We know current needs to go to current.next. But since current will be overridden here, before it being overridden, we want to assign the value to previous. In Python, this works. Now, if you are in another language like Java, where you can do this multiple assignment at once, you can just use a temporary variable, right? So you can keep track of the previous value before overwriting it with a temp variable. Should be pretty straightforward to do. And then for next, what should next be? Well, next is just the next of the previous next, right? So it's just next dot next. Okay. And now we can just, once we have this, we just need to do the to get the minimum and the maximum distance. Okay. So to get the maximum distance, we know it's just the first position of the critical points minus the last minus the first, right? So just the last minus the first. Now, what is the min distance? Well, we said the min distance, we just need to look at all the adjacent points and just take the minimum difference. So that's exactly what we are going to do. So let's just take the two that are next to each other. To get the two, we can just do a zip between the original list and the original list without the first element. Should be pretty straightforward. You can also do it with a for loop if you want to, and just compare I plus 1 minus the value at I plus 1 minus the value at position I. And here we just need to get the difference between the largest one and the smallest one. So we take the min of all of them, and this is what we need to return. So we take the min distance and the max distance. Now, something we need to do here is what if this here had 0 elements? So maybe there is no critical point, or there is only a single critical point. Then that doesn't really work. So we need to make sure that this has at least 2 critical points. So we do like this, and then if there is no critical point, we return -1 like this. And then we can run this, and we can submit. And this passes, it's accepted. Okay, so this gets accepted. Now, in terms of time complexity, we are just doing one traversal to the linked list, so that's O(n), except for, so O(n) time. Now, for space, we are using this array, which could be of n-2, right, if every element was a critical point. Yeah, so that's pretty much it for this problem. You could get rid of the O(n) space complexity here, but just for the sake of simplicity, I think this is good enough. Thanks for watching, and see you in the next one. Bye.